So we've seen Bloom filters and we've analyzed them to the point where we understand their false positive rate. And we decided that if we make an optimal choice for k, the number of hash functions, we end up with a filter that's about 50% full. We expect it to be about half set bits, half unset bits. And this gives us an excuse to talk about coupon collector, which is one of the special cases of the balls and bins way of thinking, because that's going to help us to analyze how many items it takes to make a filter 50% full of set bits. Or we can even use this framework to think about different fractions of set bits, including 100% set bits. Okay. So let's say we've chosen our n and our k, and we've got our target, because we know that this is the sweet spot, right? If we were to choose everything optimally, the filter would be half full. So in a scenario where our n and our k have been chosen a certain way, what's the expected number of items, m, or in the balls and bins regime, what's the number of balls that would get me to 50% occupancy, 50% of the bins non-empty? That's a little bit like the other empty, non-empty questions that we asked before. And as we said, for the empty, non-empty type questions, our approach, our model, is going to be this special case of the balls and bins model, which is called coupon collector. So let's dive into what coupon collector is. Okay, so the scenario is this. We have to collect n coupons. The way we do this is through a random process. So we open a box of cereal. The box of cereal has a coupon in it. The coupon is random. It's one of the n coupons chosen randomly, uniformly randomly. And this process is independent in that each new box is an independent draw to see which of the n coupons I get. It's a little bit like, so the analogy is something like prizes in cereal boxes. I thought that was maybe a little bit outdated, so I'm going to update it to Pokemon cards. So let's say we're getting Pokemon cards, we're buying Pokemon cards, we get a random Pokemon card, okay? And we'd like to be able to collect a certain set of them, like let's say these 4. And let's say every time we draw a new Pokemon card, we get one of these 4 uniformly at random, and each of our draws is independent. The question is, how many draws till we have them all? How many do we have to get until we have them all? Okay, so let's think about this process, because it's not as simple as flipping a coin or rolling a die, because there's a process whereby we accumulate more and more cards. And as we accumulate more cards, the probability that our next draw is going to be a success, that we're going to get another new card, that's changing as we go along. So it's not quite as simple as rolling a die or flipping a coin. So let's analyze it a little bit more, sort of as a timeline of what's happening. All right. So let's say here I am opening my boxes or drawing my Pokemon cards, right? So I'm opening a box with a Pokemon card in it. And I'm going to take the horizontal here to be the process of opening many boxes or drawing many cards. First box, second box, third box. It's going to go like that. And I'm going to imagine doing this many times. So I'll do this, and then I'll start over, and I'll do it again. And of course, this being a random process, I'm going to get different results each time. So let's just write down what happens in trial 1. Let's present a scenario for what might be happening in trial 1. Let's say in trial 1, I do this. Right? So this is the first box I open, and it's got Charmander. Great. This is the second box I open. It's got Pikachu. Great. This is the third box I open. It's got Eevee. Fourth box I open. It's got Squirtle. I got all 4. And this is the best possible outcome if you're in a hurry, right? Which is that the first 4 boxes each yielded a distinct card. Now I've got all 4. The process is done. So in this particular run of the random process, it took 4 boxes. Okay? And I can write down beneath here, I can write a separate series, which is up to each point in this process, how many had I collected so far? So let's say up to and including the first box, how many did I collect? Well, I collected one distinct coupon, Charmander. How many up to the second? Well, now I added Pikachu, so it's 2. How many up to the third? I added Eevee, so it's 3. How many up to the fourth? I added Squirtle, so it's 4. Okay, so it's a very simple process there. It goes up by 1 each time. Okay, that was one scenario. That was one trial. Let's do a second trial. Okay, this one's more complex because... Okay, this one's more complex because I don't get... I get repeated cards, right? So in the first step, here, I opened the box, I got Charmander. So now I've got 1. Then I open the second box, I get Charmander again. So how many have I collected? I've still only collected 1. I've still only got Charmander. Then I go to open the third box and, ooh, I got Squirtle, so now I've got 2. I go to open the fourth box and I've got Eevee, so now I've got 3. I go to open the fifth box and it's Squirtle again, I've still got 3. Go to open the sixth box, I get Charmander again, I've still got 3. Open Pikachu, I've got 4. Okay. And so on. Let's imagine a couple more trials here. Right, so some of the trials, so this is in some sense the ideal trial. That's as quickly as I could possibly get the 4 cards. But as you can see, the trials can go on for longer, substantially longer. Okay. So we want to be able to characterize sort of like the random variable that represents this process, this coupon collector process. So that ultimately we can answer the question, how many boxes do I have to open? How many cards do I have to get before I collect them all? Okay. So more formally, again, let's think of it as a random variable, x. Capital X, we'll call this the coupon collector random variable. It's the random variable representing the outcome of how many boxes did I have to open in this coupon collector context, where there's n things to collect, and I collect them via uniform and independent draws. Okay? So like we said before, what makes this scenario a little bit more complicated than average is that we are collecting coupons. The probability that the next draw is going to yield the next coupon is changing as we get more of them. As we collect more, it gets harder to collect the next one. Okay? So in other words, the process is divided up into what we might call stages by the number of coupons that we've collected so far. So for example, let's say at the outset, I'm in stage 0. Okay? And then once I've collected the first coupon, right, because the first draw always yields a new coupon, right? The probability that we get a new coupon in the very first draw is 1. So that 0th stage, or that first stage, is done immediately upon the first draw. Okay? Then I go into the next stage, the stage where I'm already holding 1 coupon, and now the probability that I get a new one as I open the next box is n minus 1 over n, right? I had to do minus 1 because I'm already holding one of the coupons. So in that case, well, that next stage goes to this point in these 3 trials, right? It goes to here in the first trial, to here in the second trial, to here in the third trial, and so on, right? So then I hold 2 coupons. So here's the stage that ends once I've drawn the third. Now I hold 3 coupons. Here's the stage that ends once I've drawn the fourth, which is the end of the whole thing. So if we think of this process as being divided into stages in this way, it gives us potentially a way of characterizing the coupon collector random variable as a combination of what's happening in each of the stages, or more specifically, it's just this. As we'll see, the expectation of the coupon collector random variable can be thought of as the sum of the expectations of what's happening in each stage. Okay, so let's build this random variable and its constituent random variables, and let's start by discussing a very simple but important kind of random variable, which is a Bernoulli random variable. In fact, we've basically seen it before because the flipping of the loaded coin, a coin where heads is more or less likely than tails, is the scenario of the Bernoulli random variable. We'd say a random variable x is a Bernoulli p random variable. P is a parameter. So a random variable x is a Bernoulli p random variable if it takes value 1 with probability p, or 0 otherwise. Otherwise meaning with probability 1 minus p. Okay, so p is the probability that we get the outcome 1, and let's just say 1 is heads. In the case of a loaded coin, let's just arbitrarily choose 1 to mean heads. So if we had a fair coin, would this be a Bernoulli random variable? Yes. P would be equal to what? P would be equal to 1/2. So a fair coin would be a Bernoulli 0.5. I just plugged in 0.5 for P. 0.5 for P. So that would be a Bernoulli 0.5 random variable with heads equal to 1 and tails equal to 2. And then a loaded coin where landing heads happens with probability 0.75 or 3/4. That would be a Bernoulli 0.75 random variable where the 0.75 again is just that parameter P. Okay? All right, so P is the chance of heads. P is the chance of heads, which takes the value 1. So what's the expected value? What's the expected value of a Bernoulli random variable, a Bernoulli P random variable? That's just P, right? That's simple. So the way we would calculate this in full would be, well, it's the probability of the outcome heads equals 1 times 1, since that's the value the random variable is mapping that outcome onto, plus 1 minus P times 0, the other outcome. But of course that just equals P, right? So the expected value of a Bernoulli P random variable is P. Okay, now that's a good stepping stone because loaded coins is a fairly good way of thinking about the situation at a given step of the coupon collector process. If we're holding a certain number of coupons, then the chance that the next draw gives us a new coupon that's not already one that we've collected, it's a little bit like flipping a loaded coin, right? And the loadedness of the coin depends on the fraction of coupons yet to be collected. So here's another random variable that builds on the idea of a Bernoulli random variable called a geometric. A geometric P random variable, just like Bernoulli, it has a parameter, one parameter called P. So a geometric P random variable x is the number of trials of a Bernoulli P random variable up to the first success. Success means the outcome of 1. In the loaded coin example, it means heads. So it's like the number of flips until we get the first heads for a loaded coin with probability of heads equal to P. Okay? So if we have a geometric P random variable and we want to ask this simple question, which is what's the probability that the geometric P random variable equals n, right? So let's say it's a fair coin. I want to know what's the probability that it takes me 3 attempts before I throw heads, right? That kind of question. Well, then we can write down that probability. We're writing down essentially part of the probability mass function for this geometric random variable. So the probability x equals n equals, well, we'll start with there's a chain of failures, right? So for the loaded coin, there's a chain of 0 or more times when we're flipping tails, tails, tails. Then there's the success where we finally flip heads. So we're just going to multiply the probabilities of those various events together. So let's first of all multiply the tails, tails, tails together. So what's the probability of tails? It's 1 minus P. And how many times do I flip tails? If n is the number of times before I have success, then n minus 1 is the number of times I have a failure, a tails. followed by the success. And that success has probability P. Okay, so these are the failures, right? Meaning tails in the loaded coin analogy. And then this is the final success, meaning heads in the analogy. Okay, so what's the expected value of a geometric random variable? It's 1 over P. Okay, so let's think about that. So if I, for example, have a random variable y, and it is a geometric, let's say 0.1 random variable. So I have a loaded coin that's heads only 10% of the time. Okay, and now I'm defining a geometric random variable. How many flips before I get heads? Well, the expected value of that geometric random variable y is going to be 1 over 0.1 equals 10. Makes some intuitive sense. If the coin lands heads with probability 10%, the expected number of times I have to flip it before I get heads is 10. So let's now return to the question of how to model the coupon collector scenario with a random variable. So we already said we would call the coupon collector random variable x. So let's just keep calling it x here. And what I'm suggesting to you is that the coupon collector random variable x can be thought of in terms of a combination of what's happening in each of the stages, right, after holding a certain number of coupons. Right, so I'm going to write x as this mysterious sum, and we'll fill in the details about what this big X sub I is. But this sum over whatever's happening in the various stages of the coupon collector process as we collect more and more coupons. Okay, and it's straightforwardly just a sum of what's happening in those stages, right? And that makes sense, because if X is the coupon collector ultimate outcome, which is what's the total number of boxes I have to open, and I'm stratifying it by stage. In other words, I'm stratifying it based on how many coupons I already hold, right? I'm going to get a number of boxes in each of those stages. I can simply add them together to get the overall total number of boxes. That's what I'm doing here. Okay, so if I let these big X sub i's be random variables for the number of boxes that I bought while holding I coupons, then I can write my overall coupon collector random variable x as that sum. The sum is stratified by stage. So now let's think about those x sub i's, and can we write down the expected number of boxes in each of the x sub i's? This is now a little bit easier because, again, what's happening within each of the x sub i's is a bit like a Bernoulli, is a bit like a geometric random variable. Okay. So let's think about the stages. If I already hold I coupons, so I could be 0, but I could be all the way up to n minus 1 coupons, what's the probability that the next box has a new coupon? Okay, so if the number of coupons held is 0, then the number of coupons remaining is n, and so the probability that the next one is new is 1. That's the uninteresting first stage, right? Where, because I don't hold any coupons, of course the first box gives me a new coupon, so not so interesting. Now let's say I hold 1 coupon, and the number of remaining coupons is therefore n minus 1. All right, what's the probability that the next box, or the next draw, gives me a new coupon? Well, that's n minus 1, the number of remaining coupons, divided by n. In other words, there's a 1 in n chance I'm just going to get the same coupon again, and I have to keep drawing. But there's an n minus 1 over n chance that I'll get a new coupon. What if I hold 2 coupons? Well, this becomes n minus 2. This becomes n minus 2 over n. Oops, over n. What if I hold I coupons? Well, then this becomes n minus I, and this becomes n minus I over n. Okay. So I can just write here n minus I over n is that probability. Right, so if little p sub I is the probability that in stage I, opening the next box yields a new coupon, I can write down that probability as being n minus I over n. Okay? So that's the probability that a given box or a given draw is going to yield a new coupon. This is like the Bernoulli trial nature of the problem, is each new draw is like a Bernoulli trial with some probability p equal to the proportion of coupons that are still left. But we're interested in how many boxes get opened in each stage. That's not a Bernoulli random variable. Well, we're asking, this is like a loaded coin flip that we do repeatedly until success, which is what the geometric random variable is modeling. So this sounds like a geometric. So each of these x sub i's is a geometric p sub I random variable. And here's p sub I right here. Okay? So if we're satisfied with the expected values of things, then we just set ourselves up for success, because we said that the overall coupon collector random variable, big X, equals the sum of stage-wise geometric p random variables. And we know what the expected value of a geometric random variable, a geometric p random variable, is. It's 1 over p. So if we want to know the expected value of the geometric random of the coupon collector random variable, well, we can use linearity of expectation and sum up the expectations of those geometric random variables. So let's do that. Okay, so we've got each x sub I being a geometric p sub I random variable, and we know what p sub I is in terms of n and I. So let's see if we can write down the expected value of the coupon collector random variable. Okay. Well, we said the coupon collector random variable itself is a sum. We said sum from I equals 0 up to n minus 1 of x sub I, where that is the stage-wise geometric random variable in there. Okay. By linearity of expectation, I can now push the expected value inside the summation. I'll put the expectation here. And because I know the expected value of the geometric random variable, I can just write that in. It's n over n minus I. Okay, I'm going to keep going. I'm going to take the n out now of the sum. I equals 0 up to n minus 1 of 1 over n minus I. Okay. Now I'm going to do just a little bit of a change of the bounds of the summation. So previously I was having I range from 0 up to n minus 1. I'm now going to have I range from 1 up to n. This is basically a change of variable, but I'm not going to change what it's called. I'm going to keep using I. But now that I is defined that way, instead of 1 over n minus I need 1 over n minus I minus 1, or in other words, I'll write out n minus I plus 1 down here in the denominator. Now what do I have here? I have the sum from I equals 1 to n of 1 over n minus I plus 1. This can be simplified because if you think about what's going on in this denominator as this index variable moves from 1 up to n, it's actually going to start with 1 over n, because I will be 1 at first, so this will be n minus 1 plus 1. So when I is 1, this is 1 over n. When I is 2, this is 1 over n minus 1. When n is 3, this is 1 over n minus 2, etc. And then when I is n, this is just 1. So in other words, I can actually simplify what I'm summing by reversing it. I'll keep the index the same, I equals 1 to n. But this is the same thing as just saying 1 over I. Right? This sum and that sum are equivalent. Right? These are the same. Okay, so all that work. And all we really used, the only interesting part here was back at the beginning when we used linearity of expectation. Okay. All right, so we've got all these different forms of the expected value of the coupon collector random variable. This one's very nice, and a lot of the discussion of coupon collector goes on to discuss the relationship between this and the harmonic number and how you could model this with a function. But I'm actually going to stick back, let's see, here with this version. I like this version a little bit better because this is the one where if we control what the upper bound of what the upper limit of the summation is, we can ask a variety of questions about how full, what's the expected number of items to add before a certain degree of fullness, right? It doesn't have to be 100% full, right? The coupon collector problem, as stated, is about collecting them all. But if we want the flexibility to ask questions about collecting half, or collecting 3/4, or collecting 90%, well then this is a nice form to work with because that's just a matter of changing what's up here. So just as an example, let's shift back to talking about the Bloom filter version of the coupon collector problem. So in case you couldn't tell, the way that we translate the coupon collector scenario into the Bloom filter regime is that the slots of the Bloom filter are the coupons, and setting them to 1 is collecting the coupon, right? So say we want to, because we know this is optimal, we want to keep a Bloom filter set bit ratio near 50%. And we have n and we have k, so we sort of know how many things are going to get added to the Bloom. We know how many coupons there are. So what's the number of items that we would add until the expected set bit ratio became 0.5, right? This is a coupon collector style problem, but instead of collecting them all, we're asking about collecting half. When are half the bits set? So if we wanted to do that, we could write down this version. That's not the version we want because that's the version that asks how many boxes till I collect them all. But the only thing we need to change is this n up here that we're summing up to, right? We're essentially saying, I don't care about all, I'm not saying I want to sum up all the stages. I want to just sum up the stages up to the halfway stage, the stage that gets me halfway full. So I can just tweak what's up there. Instead of summing up to n minus 1, I could sum up to half of n, rounded up, minus 1. And that can be my coupon collector expectation, coupon collector style expectation for this question about when are half the bits set. Okay? So that's kind of, again, why I like writing it in this form, because we can just change the upper limit of the sum to ask a different version of the question. So let's move forward with both these questions, the 50% question and the 100% question. And let's see how they actually work out in a practical scenario. So let's apply the coupon collector expectation to understand what's the expected number of items we would have to add to a Bloom filter before half the bits were set or before 100% of the bits were set. And coupon collector helps us here in the sense that we can think of slots of a Bloom filter as being coupons, and we can think of setting one of those slots to 1 as being collecting that coupon. Okay, so let's say we've got a Bloom filter with 100 slots, and so half full would be 50 of the bits are set. And what would we write here for what's the number of additions until the Bloom filter is 50% full? In other words, until 50 of the bits are set. Well, we can use this expression. So you can just plug it in and execute that expression. And let's think about what the answer would be. Well, would the answer be 50? I mean, it's conceivable that we could add 50 items and each one would set a distinct bit in the Bloom filter. But of course, we also know that collisions happen, right? So the number that actually will show up in this element here will include collisions, right? In other words, collecting a coupon that we already had. So it's probably going to be greater than 50, right? So how much greater? Well, I'll just reveal it. So it's 68.82. And so it's greater. And so what accounts for the difference? Well, the coupon collector expectation is taking collisions into account. So collisions account for the difference. Okay, now how about additions until 100% full? Well, it's going to be greater, obviously. It's not going to be twice as great because it's actually more challenging to collect the second 50% of the coupons than it was to collect the first 50%, right? Each time we collect another coupon, the chance of collecting the next one keeps going down. So it's going to be more attempts until we get the Bloom filter all the way to 100% set bits. How many? Well, 518.74, right? So some number, a multiple of this many additions. Okay, so let's go down now to a larger Bloom filter. Our Bloom filter has 1,000 bits, so half set bits would be 500 set bits. How many additions until 50% full? Seems like it's going to be something like 10 times this number. So let's try it. Okay, so it's a little bit more than 10 times that number. Okay, now what goes here? Is it going to be 10 times that number? It's more. So it's clearly substantially more than 10 times that number. And the trend will continue where this number in this column will increase, not exactly 10 times the number in the previous row, but a little bit more. Whereas this column is clearly growing faster than n. It's clearly growing faster than the number of bits in the Bloom filter. It's not linear. So what accounts for this? Well, in this column here, what's happening is that the number is approaching n natural log of 2. Okay, so it's just approaching that as we go down. This last column, though, is growing something more like n times natural log of n. Okay, so it's like n log n growth. Not exactly, I say it's tracking n natural log n. But it's growing with something like n log n type growth. So why is that? Well, I'll leave this as an exercise, but I'll just give a couple of quick hints. So for this column here, what's the reason why it's approaching n times natural log of 2? Well, that should become clearer if you go back and look again at the formula we wrote down for tilde p sub 0. That relates tilde p sub 0 and k and m and n. And then think about this scenario where k is 1 and n is n, and m is the thing we're trying to calculate the coupon collector expectation for. And you should see that this makes sense, that n log 2 makes sense. The hint for this column here is that, like we said, that final way that we wrote the coupon collector expectation, where we said n times the sum from I equals 1 up to n of 1 over I, well, that sum of I equals 1 up to n of 1 over I is something called the harmonic number. And so people have studied how does the harmonic number grow with n, and that will tell you why this one tracks with n times natural log of n.